Hello everyone, as you all know, I am Anupriya, currently pursuing my BE degree from Shri Venkateshwara College of Engineering. So today we have assigned the topic classification of signals. So let's see each and every topic and let's try to understand what are the classifications of signals and how they are classified. Introduction to signal classification. Signal classification is essential for understanding how to process and analyze data. Signals can be categorized based on their characteristics and behavior. This classification aids in selecting appropriate techniques and for signal processing. So now we can see that signals are classified into two, linear and nonlinear. Further, linear is classified into four groups: stationary, non-stationary, Fourier transform basis, Velvet transform basis. And nonlinear is classified into the one which is Hilbert transform basis. So we'll be studying all these things one by one. The first one which we have is continuous versus discrete signals. Continuous signals are defined for every instant of time and can take any value. Discrete signals are defined only at specific intervals and represent sample data. The distinction impacts how signals are analyzed and processed in various applications. Here you can see the continuous versus discrete spectrum. The four difference which we have is definition, structure, appearance, and example. You can study by yourself this one. Next one we have deterministic versus random signals. Deterministic signal can be precisely defined and predicted over time. Random signals are inherently unpredictable and characterized by probabilistic behavior. Understanding this difference is vital for applications and communications and control systems. Applications in communications and control system. Now here we can see the waveform of deterministic signals and random signals. As deterministic signals are precisely defined and predicted, we can see the signals are equally distributed, while the random signals are not not they are not they are unpredictable and uncharacterized, so we can see the randomness in the waveform. Moving on, we have periodic and aperiodic signals. Periodic signals repeat at regular intervals, showcasing a consistent pattern over time, while aperiodic signals do not exhibit repetition and can vary significantly over time. The classification plays a crucial role in signal analysis and Fourier transform. Here we can see the periodic signal waveform as well as the non-periodic signal waveform. Periodic signal is at regular interval and at equal and is divided equally over the time period, while the non-periodic is completely different to the periodic signal. Now we have analog signals versus digital signals. Analog signals are continuous in nature and can represent a wide range of values. Digital signals are discrete and consistent of binary values, typically representing sampled analog signals. The transition from analog to digital processing has revolutionized modern telecommunications. Here we can see the analog and digital signals waveform. The analog has the waveform like the sine wave, and the digital one has discrete like the in the rectangle form, and like the another one which is drawn as the waveform of analog signals and the discrete signals. The discrete one has like the stairs one, and the analog is like more like a waveform. Now we have energy signals and power signals. Energy signals have finite energy and zero average power over time. Power signals have infinite energy but finite average power over time. This classification is important for understanding signals behavior in different systems. Now we have real versus complex signals. Real signals consist of real numbers and can be easily visualized on a one-dimensional plane. Complex signals include real and imaginary components, providing more information about the signals. Complex representation is often used in advanced signal processing techniques like modulation. Here we can see the complex number, which is divided into two groups: real numbers and imaginary numbers. Real numbers are the one which is uh, at the left side of the complex number, and the complex and the imaginary numbers are the one which is in the form of j. Moving on, we have baseband and bandpass signals. Baseband signals occupy a frequency range starting from 0 up to a certain maximum frequency. Bandpass signals are restricted to a specific frequency range, excluding low and high frequencies. This classification is crucial for communication system and filter design. Here we can see the baseband signal and the broadband signal. Baseband signal is a single signal which is passing from one to another, and while the broadband signals are the one in which like more than one signal is passing from one to another. Last but not least, we have unipolar and bipolar signals. Unipolar signals have values that are either positive or zero, simplifying their representation. Bipolar signals can take on both positive and negative values, providing more information. The choice between unipolar and bipolar affects encoding schemes in digital communication. Now, let's try to cover all the topics which we have studied in this video as conclusion and applications. Understanding signals classification is fundamental to effective signal processing and analysis. This knowledge is applied across various fields, including telecommunications, audio processing, and control systems. As technology evolves, the methodologies for classifying and processing signals continues to advance. Thank you everyone for watching my video. I hope you guys like it, and we'll meet in our next video. Till then, bye bye.